4.6 Similarity and Transformations. Our essential question is, when a figure is translated, reflected, rotated, or dilated in the plane, is the image always similar to the original figure? Alright, what you're going to learn is we're going to do some similarity transformations, and we're going to also describe them, what it means to be similar. So, here's this nice paragraph for you to read. Dilation is a transformation that preserves shape but not size. So we call dilation a non-rigid motion. A similarity transformation is a dilation, a composition of dilations, or a composition of rigid motions and dilations. So basically it's everything we've done with transformations in this chapter so far. Two geometric figures are similar if and only if there is a similarity transformation that maps one of the figures onto the other. Similar figures have the same shape, but not necessarily the same size. That's the important thing. That's what I would highlight and make sure I write down and I know. Similar figures have the same shape, but not necessarily the same size. Okay. When the scale factor of dilation is not equal to 1 or -1, similarity transformations preserve the angle measures only. That's another important thing to write down and to have an understanding of. Alright, so let's get down to it. We're going to perform a similarity transformation and see what that actually looks like, and try to get some understanding, get a concept of, or a grasp of what that just meant. Alright, so first things first, we're going to graph the original triangle ABC. Alright, so there it is. And now we want to do the translation. So we're going to take each value, we're going to go 5 to the right and 1 up. Okay, so translating that, we went up 5, or right 5, up 1. All right, and so these are my new coordinates after the translation. So I want to take these coordinates now, and I want to dilate it with a scale factor of 2, and I'm going to use 2, -1 as my center of dilation. All right, so using our formula that we got from lesson 4-5 dilations, I'm going to take my scale factor, which is 2, and I want to multiply that times my x value, which is 1, minus my a, which is 2, plus 2. That's going to give me my new x value. Then I want to do that again for my y value. I'm going to do 2, because that's my k. Then I'm going to take my y value, which is 2, minus my b value, which is a -1, and then I want to add my -1, alright, and so that is going to give me my new value for the dilation, which is going to be then a double prime. Simplifying that out, that gives me the new coordinates of 0, 5. Okay, and if I continue this for B and C, doing the same thing, B double prime is going to come out to be 4, 7, and C double prime ends up being 4, 5. So let's graph it. Okay, so here's our image now after our dilation. So notice this is considered a similarity transformation because it's the same shape, it's a triangle, and actually it's a right triangle, but notice that it's not necessarily the same size. At this stage it was the same size, but then we dilated it, enlarged it, and so this kind of path going from here, translation to dilation, that's a similarity transformation. Right, now we want to look at a different type of similarity transformation. We're going to do a composition of dilation, and what that means is we're going to dilate the pre-image once, then we're going to take the new image and dilate it a second time. And so here we go. Let's see what this looks like. Alright, so there's our original triangle MNP. Now I'm going to take that P in that coordinate for M, which is at -6, 4, and I'm going to use the center of dilation at 2, 2. My scale factor K is 1/2. Now that's going to map my coordinates. And what I want to do real quick before that, remember that this is going to be your A, this is your B, and then your K. So if I'm mapping these points, or as I'm mapping these points, I want to use this formula. I want to translate it. I'm going to kind of do a generic thing. This is going to be 1/2. I'm going to take my X value, and I'm going to subtract my A, which is 2. And I want to add the 2. Then for my Y's, I'm going to have 1/2 Y minus 2 plus 2. Alright, so that's the generic form for these 3 points. All I'm going to do is I'm going to substitute my -6 here, and I'm going to substitute my 4 here, get the values of M. I'm going to do the same thing with N. Now I'm going to substitute -4 in this spot. I'm going to replace that with -4, and I'm going to replace this one with 4 here. This would be my XY, my XY, and my XY for all 3 of these. So punching that into the calculator, we're going to get that M prime is going to be at -2, 3. Okay, and then N is going to be at coordinates -1, 3. P prime is going to come out to be 2, 4. Okay, let's graph that. Okay, we get this smaller triangle here. Now for the second dilation, we're going to do the same thing, except here's my A, here's my B. This scale factor is 3. So this was the first dilation. Now for the second one, we're going to use this XY. We're going to do the same thing, except our scale factor is 3 now. So we're going to do 3 times X minus my A. In this case, it's going to be 1 plus 1. And then for the Y values, we're going to do 3Y minus 5 plus 5. Okay, so same idea. I'm just I'm switching my K's for 3, my A for 1, and my B for 3. That should be my B's for 5, is what this should be. Alright, and so using those coordinates, with AB being at 1, 5, my M double prime ends up being -8, -1. N double prime comes out to be -5, -1. And P double prime ends up being 4, 2. Okay, so let's graph that. Alright, so this is our final dilation, our final image. We went from this pre-image to this mid dilation, and then the final image is this triangle M double prime, N double prime, P double prime. Alright, this last example is going to want us to kind of figure out how we got from this original image PQRS, the pre-image, and rearranged it and got this other trapezoid WXYZ. Just looking at it off the top, looks like they're facing each other, so it looks like this has to be a reflection centered about the y-axis. So let's write that down. Trapezoid PQRS is reflected across the y-axis. Okay, it looks like that's what happened first, and then obviously it's smaller, so we got to kind of compare these sizes. So if I look at the length of PQ, that's 3 units, and XW has a length of 1. Looking at the height of WZ, that's 2 units, where the height of PS, that's going to be 6 units. Alright, so kind of looking at this as a ratio, it would be 1 to 3 if I'm looking at XW to PQ. Just to confirm that, see if there's a pattern, if this works. WZ has unit length of 2, PS has a length of 6. That does reduce to 1/3. Okay, so this looks like it is a dilation then we'd say P prime, Q prime, R prime, S prime. Got to say this is trapezoid. Trapezoid PQRS prime is dilated by a scale factor of 1/3. Alright, and then we want to make sure that the center of dilation is the origin. And if it is, then all we have to do is multiply our scale factor with our coordinates. Now, remember that P, if we look at this, P is at -6, 3. And we said that it was a reflection across the y-axis. So if I reflect that, P prime is going to be at 6, 3. Okay, and then so I want to take my scale factor, kind of double check this. If I'm right, that then W would be what I end up with, the coordinates for W. So I'm going to take my scale factor, I'm going to take 1/3 times 6 for my x value, then I want to do 1/3 of 3, and then 1/3, that gives me 2, 1/3 of 3 is, 1/3 of 6 is 2, 1/3 of 3 is 1. Alright, so that would be kind of my double, or my P double prime, which if I look at W is at 2, 1. Right? And those match. Because those match, that tells me that my center of dilation is 0, 0. So let's write that with center of dilation. Center dilation at 0, 0.